Coulomb's law is something you can use to explain trends in ionization energy. And it looks real fancy. It's this cute little equation here. But it really summarizes what we've mentioned in previous videos. Now, Coulomb's law is an equation, but you're not going to need to do calculations with it, meaning that it's not in the AP packet. But you will want to reference Coulomb's law or understand what it refers to. Now, this definition is kind of a mouthful. Coulomb's law states that the force, we're talking about an attractive force, between two particles is proportional to the magnitude of the particle charges and inversely proportional to the square of the distance between the two particles. Yikes. Okay, here's what we're looking at. Take two atoms. How about boron versus neon? And now, when they talk about charge of two particles, in an atom, we're referring to like the charge of the nucleus versus the charge of the electron cloud. So the electron cloud itself isn't like a particle, but we're comparing like the positive charge versus the negative charge. So we've got 5 protons and 5 electrons versus 10 protons and 10 electrons. And so now we've said that the neon atom has a greater nuclear charge, which means greater attraction. Greater attraction between the nucleus and the electron cloud. That's what Coulombic force kind of refers to. An attraction between the positives and the negatives. Or in this case, the electron cloud versus the nucleus. Okay, so now let's look at this as an equation. E stands for energy. In this case, we're going to use ionization energy. If the charge values on the numerator side of this equation are larger, so we're talking a plus 10 and a minus 10 versus a plus 5 minus 5, we've got larger charges in the neon atom. That should create an E value that's also larger, right? So if the value in the numerator is larger, E is larger. If E is ionization energy, that makes sense. That, yeah, in the neon atom with the greater attraction, it's going to take more ionization energy to remove an electron. Oh, well, that's not so bad. I mean, that's not what we've talked about in the past. But now we're just using this equation to, again, kind of summarize that. So Q1 and Q2 refer to the charges. It's going to be a balance between the positive charge and the negative charge. As those charges increase, there's a greater attraction, which means we're going to need more ionization energy to remove electrons. Now let's look at R. The R value stands for the distance between two particles. Or when we're talking about atoms, think about R as like the radius. Distance between particles. Think about it as the radius. We're really referring to like the radius of the atom, the distance between the nucleus and the furthermost electrons. So let's look at two extremes. Lithium versus cesium. And we'll just do kind of like a cross section. This is exactly what atoms look like, right? Positive nucleus. Lithium has electrons distributed amongst two energy levels. So this is kind of like my R value. R. La, la. Cesium, here's my positive nucleus. Electrons are distributed among 6, 2, 3, 4, 5, 6 energy levels. So now this is kind of like my R value. So my R value is larger. There's a larger radius in cesium. What does that mean in terms of like attraction between the electrons and the nucleus? It's a weaker attraction. If I had a valence electron out in that 6th energy level, the attraction to the nucleus is pretty small. Number one, it's just far from the nucleus. Number 2, the shielding effect. All those inner electrons are going to block the attraction between the nucleus and that outer electron. So now look at this numerically, and it's in terms of this equation. As the denominator increases, as the radius increases, the value of E decreases. Oh, so yeah, like in an atom with a large radius, ionization energy is small. Now again, that's just a way of rationalizing these trends using Coulomb's law. And again, when they refer to Coulombic force, or maybe they'll use like the term Coulombic attractions, in an atom, it's just referring to the attraction between the nucleus and the electron cloud. So again, a lot of these trends make sense, and we can explain these on an AP test. This might be a good free response question, a no calculator free response kind of question. So going down a group, ionization energy decreases. The atoms get larger, so there's less attraction within the atom. But then if I compare two atoms like going across, maybe lithium and neon, for example, the ionization energy increases quite a bit. Now going across from lithium to neon, we're just filling the second energy level. But as I add an electron, I'm also adding a proton. So the nucleus in the neon atom is more positive, greater nuclear charge, meaning that there's more attraction between the nucleus and the electrons. Greater Coulombic force within the atom. So as I go across and the atoms get smaller, it takes more energy to remove electrons. Piece of cake, right? It makes total sense. Now here's another thing you might see, like maybe multiple choice kind of question on the AP test. A, B, C, D, well, there's not D in this case, just 3 choices. Which has the greatest first ionization energy? And which will have the smallest second ionization energy? Well, first I should probably figure out what these atoms are, right? This guy is element number 10, neon. This is 11, sodium. And 12, magnesium. Greatest first ionization energy means which of these will require the most energy to remove the first electron, the outermost electron. Okay, well, sodium would like to remove 1 electron. Magnesium, he'll get rid of 1, and he'd actually like to get rid of 2. But look at neon. Neon doesn't want to lose any. All of his electrons are paired and the orbitals are full. We don't want to remove 1 electron. We don't want to remove any electrons from neon. Smallest second ionization energy kind of means like who would like to lose 2? Well, it's obviously not neon. Sodium would like to lose 1, but losing 2 means that we're going to the core electrons. We don't want to do that. So it's magnesium. Yeah, he'll lose 2 electrons, no problem. So that might be a good example of how you might see something like this, like multiple choice style. Now here's the last thing we should mention in terms of ionization energy. Obviously they're going to ask you to rationalize and explain trends. And sometimes that's pretty obvious. They'll give you trends that work out exactly what you would expect. They might say like, why is the ionization energy of helium greater than radon? Well, duh, actually, it makes sense. All the noble gases are listed here and they make sense. Neon's the smallest atom. It's going to have the greatest attractive forces, smallest radius, I should say. The greatest attractive forces within the atom means it's going to require the most energy to remove an electron. As I go down toward radon, he's got electrons in 6 energy levels. There's going to be some shielding going on between the nucleus and the outermost valence electrons. I mean, none of these guys want to lose electrons, but especially a small atom like helium. And as I go down the group and the atoms get bigger, it would be easier to remove electrons from radon. The ionization energy is less. There's just less attraction within the atom. Same thing if I look at like the alkali metals, lithium down to cesium. As I go down a group, ionization energy decreases for the same reasons. Now they could also ask me to compare something like, why is the ionization of energy of neon greater than lithium? And we'd say, okay, well, these guys are going across a period, so they're both filling the second energy level. Now, you could say something about, well, lithium would like to form a +1 ion. We could say something about how as I go across toward neon, the atom is very stable, the orbitals are full, everything's paired. Now, we don't want to lose electrons. That wouldn't form a more stable particle. Or especially I'd want to think about explaining this in terms of Coulombic attraction. That when I go across, neon's got more protons and more electrons. So even though those electrons are still in the same energy level as lithium, they're the same distance from the nucleus in general, if the neon nucleus is more positive, there's going to be a greater attraction for the electrons. So neon is a smaller atom. It's going to take more energy to remove the electrons. Smaller radius, I should say. So again, as I go across a group, that trend makes sense looking at this graph. However, there are some kind of bumps along the way. And of course, those are ones that they'll also ask you to rationalize. Here's one example. Look at in here. As you go across from beryllium to boron, beryllium is element number 4, and boron is element number 5. So you would expect boron to have a greater attraction between the 5 protons in the nucleus and the 5 electrons versus beryllium, who's only got 4 protons and 4 electrons. So if there's more attraction within the boron atom, you'd think it would be a smaller radius, more attraction, require more ionization energy. And it's less. Oh, brother. So if you have to try to come up with some explanation of why this doesn't follow trend, think about the atomic structure of the atoms. And I usually like to either rationalize it by kind of referring to an electron configuration, or maybe even like a rough sketch of an orbital diagram. 2s. Okay, so here it'd be beryllium, and then let's do boron. 1s2, 2s2, 2p1, or a rough sketch. There's like the 1s and the 2s. And here are the p's. 2p. So I'd have 1, 2, 3, 4, 5. Now you don't have to memorize these exceptions to the rule. They'll tell you. They might give you a graph like this and say, hey, what's up with this trend between beryllium and boron? Why is boron's ionization energy lower? You don't have to know that off the top of your head. Or maybe they would give you numerical values. This is the ionization energy of beryllium. This is the ionization of boron. Why is boron less? Okay, so in other words, we're saying that it's easier to remove an electron from boron. So I got to try to think of a logical explanation. Well, number 1, paired orbitals. Let's say like paired electrons in full orbitals. That's stable. So there is something kind of stable about the beryllium electron configuration. Now I get it. The second energy level is not completely full, but the outermost orbital is full. So there is something stable about the beryllium electron configuration. All the electrons are paired and the used orbitals are full. Okay, so now let's look at boron. We've got 1 electron in this 2p orbital. The 2p orbital is a little bit higher energy orbital. So this electron in the p orbital is in a little bit more of an unstable situation, a little bit more of an unstable orbital versus s orbitals. Okay, so right away there, that might mean that it's easier to remove this p electron. It's in a higher energy orbital. Higher energy is always unstable. So we can put that in here, that this guy is in a higher energy orbital. And that would just naturally be unstable. Or less stable, I should say. The other thing that they kind of mentioned too is the shielding effect. So let's pretend that, you got your nucleus. Well, right in here you've got full s orbitals. The 1s and the 2s are full. Shielding effect. So you've got these full s orbitals that are going to block the attraction from the nucleus to the outermost electron. Meaning, again, that it could be easier to remove that outermost p electron versus trying to remove a paired s electron. Interesting, huh? So again, we can rationalize these trends or exceptions to trends by thinking about atomic structure and kind of knowing like what's stable. Stable is having full orbitals, paired electrons, lower energy orbitals are always more stable, and all of those don't really apply to the boron atom in the same way that they do the beryllium atom. Another exception, check this out, going across from something like phosphorus to sulfur. Phosphorus to sulfur. Well, as I go across the periodic table, again, sulfur is element 16 versus phosphorus number 15. Sulfur should have an extra proton, an extra electron, greater attraction. It should take more energy to remove an electron from sulfur. And it doesn't. Same thing kind of happens up here with like nitrogen and oxygen. So I got to try to figure out why. And I like to think about electron configurations and orbital diagrams. Okay, so they kind of give us the electron configurations, or at least the valence electron configurations of phosphorus versus sulfur. But let's sketch these into an orbital diagram. So we'll only show the valence electrons. So here's phosphorus. We'll do the 3s. And then here would be the p's, 3p. And then here's sulfur, the 3s. And then here's our 3p's. 3p. Okay, so we've got 2 electrons in the s. And now here, this is where, again, you got to understand your orbital diagrams. Phosphorus should have 3 electrons in the p orbitals, but we would fill them one at a time so they all get their own orbital. Now with 4 electrons, you're going to have to pair them. 2, 3, 4. And obviously the s is full. Okay, so we're saying that it takes less energy to remove an electron from sulfur. Why? And why would it be easier to remove an electron from sulfur than phosphorus? Okay, now with these p orbitals, there are 2 stable options. We either want them all full or we want them all half full. So like with phosphorus, having 1 electron in each of those p orbitals, that's actually pretty stable. We either want 1 in each of the orbitals or we want them full with 2 in each of the p orbitals. But with sulfur, when we had to go up back here and pair them, this is going to cause repulsion. There's going to be a little electron repulsion. It would be more stable to have 3 p electrons versus 4. Ah, interesting. So that electron-electron repulsion actually makes it easier to remove an electron from sulfur. The p orbitals in phosphorus are more stable, with them all having just one electron. So they don't have to worry about any extra repulsion. We want them either all full, or in this case with the p's, we want them all half full. And so that's kind of what they're explaining here. There's some electron-electron repulsion between the two paired electrons in sulfur, and that's going to create a smaller ionization energy within the sulfur atom.